the steam giant that had no pistons. This is why the turbine-drive was a mechanical fever dream. For over 100 years, every steam engine in the world worked the same way. You had a massive piston pushing a heavy rod. It went back and forth. It went chuff-chuff. It was the heartbeat of the world. But in 1944, the Pennsylvania Railroad decided the heartbeat was too slow. They built a machine that did not have a single piston. It did not have rods. It did not make a sound like a train. Instead, it hissed like a jet fighter. It had a massive turbine that spun at thousands of revolutions per minute to create 6,000 horsepower of glass smooth energy. It was supposed to be the future. It was supposed to be the engine that killed the diesel. But inside the giant gearbox, a secret flaw was waiting to turn this dream into a pile of jagged shrapnel. Why did the world's smartest engineers build a machine that was too smart to actually work? And what happens when you try to turn a locomotive into a 600-ton spinning top? A piston-driven locomotive is a machine at war with its own physics. Every mile, tons of steel surge back and forth, reciprocating mass, connecting rods, crossheads. Each stroke throws force into the rails, not just forward, but down and up, hammering the track with every revolution. This is the hammer blow. At speed, the effect grows violent. A single main rod on a fast passenger engine can hit the rail with more than 10,000 pounds of vertical force, enough to crack ties, loosen spikes, and send shockwaves through every joint. The rails flex, the wheels pound. Maintenance crews chase cracks and bent plates from Chicago to New York. The American Association of Railroads sets limits, but the reality is simple. Above 60 miles per hour, the violence is exponential. The faster you go, the more the track suffers, and the more the locomotive shakes itself apart. Railroads pay the price in downtime, derailments, and endless repairs. A high-speed run means 20 to 30% higher track wear and wheel set replacements. Shop time multiplies. The maintenance burden is relentless. This is not just a problem of comfort or cost, it is a hard ceiling on speed and power. The reciprocating rod is the enemy of smoothness. The piston is the enemy of the future. The S2 eliminated the hammer blow of the reciprocating rod. It replaced violent vibration with a steady, high-frequency hum that felt like the future. No chuff, no pounding, just the hiss of steam and the whir of reduction gearing. The engineering was a masterpiece of precision, but the environment was a war zone of coal dust and steel. The fever dream of the designers was no match for the reality of the rails. Diesel was easier. The S2 was a beautiful failure, but it aimed for the stars. Silence where thunder should be. The S2 announced itself not with the pulse of pistons or the deep drum of exhaust, but with a sound that belonged to another age. At rest, it waited, a giant of steel and steam, yet still. When the throttle opened, there was no chuff, no echoing heartbeat of cylinders. Instead, a rising hiss. A turbine winding up, drawing power from superheated steam, translating pressure into rotary motion with no pause, no reversal, no hammer blow. The rails did not shudder beneath a piston's violence. The track felt only the smooth, even pull of gears and axles. To stand beside the S2 was to witness a machine that defied the script of American railroading. The absence of reciprocating mass was more than a technical detail. It was a sensory shock. The high-frequency hum of reduction gearing replaced the familiar racket with a continuous, almost ethereal vibration. At speed, the locomotive seemed to float, its motion a single, unbroken flow of energy from firebox to rail. This was not an incremental improvement, it was a declaration. The S2 wore the keystone of the Pennsylvania Railroad, but it belonged to the mythology of the future. Its form was all streamlined casing, its drive a secret of turbines and gear trains. The rods and crossheads that had always defined the American locomotive were gone. In their place, a direct drive turbine system, engineered for purity of motion and mechanical efficiency. For a moment, the S2 seemed to promise a new kind of power. Not just more speed, but a different relationship between machine and track. The old rhythm of piston and rod was silenced. The dream was a locomotive as smooth and relentless as a river. The reality would soon reveal itself in the gears beneath, but in the hum of the S2, the piston was already a memory. The turbine at the heart of the S2 spun at 9,000 revolutions per minute. No piston, no rod, just a bladed wheel whirring at a speed more familiar to a destroyer than a locomotive. The challenge was simple in theory and brutal in practice. How do you take that blinding velocity and turn it into the slow, relentless pull of steel wheels on rail? The answer was reduction gearing. Not a single gear, but a double-stage assembly cut and hardened to withstand the violence of torque transfer. The gear train took the turbine's 9,000 revolutions per minute and stepped it down to about 500 revolutions per minute at the axle. That is an 18-to-1 reduction. Without this, the wheels would spin uselessly, or the turbine would tear itself apart trying to match the speed of the rails. Each stage of reduction had to absorb shock, distribute load, and keep backlash to a minimum. The first stage dropped the turbine speed to an intermediate shaft. The second stage brought it in line with the drive axles. Every tooth in those gears was a calculation in metallurgy and stress. Helical forms, case carburized steel, pressure angles set to minimize noise and maximize contact. Bearings carried not just the weight of the mechanism, but the axial thrust of blades biting into steam at thousands of feet per second. Forced oil lubrication kept the heat in check, but coal dust and grit were always waiting to turn precision fits into grinding hazards. A turbine wants to run free, but a locomotive must grip the rail. The 18-to-1 ratio was not a theoretical preference. It was the only way to reconcile the physics of steam velocity with the reality of steel wheels. At full speed, the blade tips raced faster than any piston rod ever dreamed. The gearbox was the bridge. Without it, the S2 would have been a stationary engine, a marvel that could never move a train. With it, the machine became something new, not a piston engine in disguise, but a true direct drive turbine. The hum of the reduction gearing was the sound of ambition made real. The gearbox beneath the S2 was a cathedral of precision, but every tooth in its reduction gears was a wager against disaster. Shop foremen remembered the tension in the air when the covers came off. The gears were helical, carved from case-hardened steel, each one ground to a tolerance of 0.005 of an inch. The forced oil system pushed lubricant under pressure through every bearing and mesh, fighting heat and friction. But the oil never ran pure for long. Coal dust drifted through the shops, settling on every surface. Grit found its way past seals and into the oil, turning the lifeblood of the machine into a grinding paste. Every contaminant was a time bomb waiting to pit a tooth, score a bearing, or seize a shaft. Alignment was everything. A gear out of true by a hair's width would load unevenly, concentrating stress at the root of a single tooth. Under full power, with the turbine spinning at 9,000 revolutions per minute, that stress could spike without warning. Fatigue cracks began as invisible threads. One misaligned shaft, one grain of grit, and the pressure would build until the steel let go. When a tooth failed, it did not fail quietly. Shrapnel tore through the casing, ricocheting off hardened walls. A single fracture could turn the reduction gear into a machine gun of jagged steel, destroying itself in seconds. The S2 demanded perfect lubrication and perfect alignment, but the world it lived in was anything but perfect. Coal dust, water, and vibration worked against the engineer's dreams. The gearbox was not just a bridge between turbine and wheel, it was a battlefield. Every mile threatened a new kind of failure. The shop floor knew it. The foreman's hands shook as he tightened the bolts, aware that one missed contaminant could mean catastrophe. The S2's reduction gearing was a triumph of design, but it lived on the edge of mechanical chaos. In the war zone of the railroad, even masterpieces could be undone by a single flake of steel. The numbers behind the S2 do not flatter, they expose. In steam engineering, performance is measured in specific steam consumption. Pounds of steam burned for every horsepower hour delivered to the rail. The S2's direct drive turbine was a marvel of stage efficiency at its design point. At 70 miles per hour, the turbine spun near 9,000 revolutions per minute. Blade velocity matched the velocity of the steam jet. Stage efficiency approached the theoretical maximum. At this speed, the S2 consumed less steam per horsepower than any reciprocating locomotive in service. The mechanical transmission lost only 3% of its energy. 97% of the work done by the steam made it to the wheels. At 70 miles per hour, the S2 was the most efficient machine on the rails. But the equations that made the S2 a marvel at speed became a trap at low speed. Turbines are creatures of velocity. Their efficiency collapses when forced to run slow. When the S2 started a heavy train or climbed a grade below 30 miles per hour, the turbine blades no longer matched the speed of the steam. Energy transfer fell apart. Steam consumption soared. The boiler could not keep up. Pressure dropped from over 300 pounds per square inch to nearly 100. The firebox strained. Staybolts failed. The crew watched the dials and felt the machine gasp for breath. The numbers are clear. Above 40 miles per hour, the S2 outperformed even a 6,000 horsepower diesel electric. At 70 miles per hour, it was a champion. Below 30 miles per hour, it became a liability. No amount of engineering could change the physics. The S2's beautiful efficiency curve was a razor's edge. It lived in a narrow band of perfection and spent the rest of its life paying the price for that ambition. The data did not lie. The dream of the pistonless future was real, but it came with a cost measured in steam, coal, and lost time. Stall was not a theoretical risk. It was a physical event, lived in the cab and the shop. On a grade, the S2's turbine demanded more steam than the boiler could deliver. Pressure dropped. The firebox roared. The dials spun backward. The crew watched the boiler gauge sink from 310 pounds per square inch to near 100 in minutes. When the turbine blades slowed, the entire machine lost its grip. The train would crawl, then stop. Restarting was agony. The reverse turbine engagement, rated at 1,500 horsepower, could not move a full consist uphill. The main turbine, starved of steam, spun uselessly. The locomotive sat stranded, silent, massive, and helpless. Its promise of relentless motion was broken by a simple law of thermodynamics. Each stall left scars. Staybolts inside the firebox, meant to hold the boiler's shape against pressure, suffered thermal shock as cold water met hot steel. Cracks formed. Repairs were constant. The high-frequency hum that replaced the hammer blow of pistons could not protect against the slow violence of heat and fatigue. Bearings designed for turbine speeds overheated. Lubrication systems, perfect on the drawing board, struggled in the real world. Coal dust turned oil into grit. Bearings failed every 500 miles. Gear teeth wore unevenly. Shop crews grew wary. The S2 returned for maintenance again and again, its beautiful gearing undone by the smallest contaminants. On the shop floor, the verdict was simple. The S2 was a machine that could not survive its own ambition. It wore out bearings faster than they could be replaced. Staybolts snapped under pressure swings. The reduction gearing, so precise in theory, became a liability in practice. The locomotive that had no pistons, no hammer blow, no pounding, became a different kind of maintenance nightmare. The war against reciprocating mass had ended, but a new war had begun. Diesel was easier. The S2 was a fever dream of direct drive power, undone by the reality of the rails. A torch cuts into the S2's boiler shell. Steel that once held 310 pounds per square inch surrenders in a shower of sparks. The turbine's heart, designed for 9,000 revolutions per minute, is silent now. Plates peel away. The gear train, case-hardened, ground to 0.5 of an inch, meets the flame. Teeth that once carried 6,900 horsepower through a double reduction now fall apart, layer by layer. No piston rods to salvage, no crossheads to save. Only the smooth-bladed core of a machine that never belonged to its time. In 1949, the S2 entered the scrapyard at Conway, Pennsylvania. The torch erased the high-frequency hum. The future, once promised in polished steel, is now a heap of fragments cooling in the yard. The mythic ambition of the direct-drive turbine ends in a pile of cut metal, the last trace of a beautiful failure. The rails keep moving. Diesel is easier. The S2's dream dissolves in the smoke, leaving only the memory of a machine that tried to master the physics of motion and found itself undone. Steel on rail. That is the American contract. For a century, the locomotive was a living thing, pistons pounding, rods lashing, every wheel a signature of muscle and noise. Then the S2 arrived. Its drive was not a rhythm, but a continuum. No reciprocating mass, no hammer blow. The rails, for once, did not feel the violence. They felt only the smooth insistence of reduction gearing and the endless turn of a turbine. The S2 did not shake itself apart or batter the track. It glided, indifferent to the old limits, as if the laws of motion could be rewritten by cleverness alone. But the rails did not ask for perfection. They asked for certainty. They asked for a machine that could start in the yard, crawl up a grade, idle in a siding, and thunder across the plains. Diesel delivered that promise. It was not elegant, it was not beautiful, but it started every time. It drank less, it stalled less, it made no mythic claims, only practical ones. The S2 was a fever dream of direct drive power. Diesel was ease. What is lost when ambition is traded for certainty? The rails remember. The S2 aimed for the stars. The final line, diesel is easier. The S2 was beautiful, but it could not survive. Today, diesel traction rules the rails. Its simplicity triumphed where the direct drive turbine demanded too much precision from an imperfect world. The S2 eliminated hammer blow and reciprocating mass, but the reality of specific steam consumption and reverse turbine engagement proved unforgiving. Beautiful failures like the S2 remind us, reaching for perfection sometimes means building machines too advanced for the track beneath them. What are we willing to risk for progress?